he has a joint appointment. He's director of Max Planck Institute and also professor of University in Munich. So he did his PhD in Mainz, and he did PhD in Munich. And then he had a faculty position in Mainz before moving back to Munich, where he is working now. Thank you very much for coming to our workshop.
Okay, so thanks Eugene for that nice introduction, and so thanks for the invitation to be here. So in this kind of next 45 minutes, I'd like to tell you about some recent experiments of our group, some on dynamics, non-equilibrium dynamics, which has kind of become one of the hot topics in the field, and also something I consider very exciting, the ability to do single site and single atom resolved imaging in optical lattices on artificial crystals of light, which I think will open really it's really a quantum jump in terms of the possibility that it offers us to analyze. So I want to go into detail into that in the second part of my talk, and I think, especially most of you being theorists, just try to show you what kind of new possibilities we have in doing that. Okay, so these are basically the three teams that have contributed to the experiments: our fermion team, our boson team, and our single atom high resolution imaging team that have contributed. We also had the pleasure to work together with a number of theorists. These are the ones which were relevant kind of for this talk, contributed to the work presented here, and also let me acknowledge our funding agencies who are supporting our work. Okay, so the three topics I would like to discuss with you are, on the one hand, dynamical transport properties of interacting fermions in optical lattices. And then I'd like to come to a topic on generalizing kind of simple ideas that we all know from two-level systems, like Landau-Zener transitions, and ask the question, can we generalize such concepts to many-body systems, strongly interacting many-body systems, and on what's going to be the same, what will change, how do they differ? And as I announced in the third part, I would like to talk about this high-resolution imaging, single-site, single-atom resolved imaging in optical lattices. Okay, so let me just remind everybody about the system we're talking about, tell you about the system. So the system is an artificial periodic potential that we create by superimposing standing waves on top of each other and loading bosonic or fermionic quantum gases into these optical lattices. We can create kind of one-dimensional potential tubes, something you can see here, to create one-dimensional geometries, where the atoms are free to move in the direction coming out of the plane of the whiteboard, and in the transverse planes they're confined to these narrow tubes, so we have really nice 1D systems. Or if we want to do 3D systems, then we just add another standing wave to create, for example, this simple cubic crystal of light, where you can think of as each lattice site being like a harmonic oscillator, and tunnel coupling between those harmonic oscillator lattice sites. So of course we can easily change from this situation to that situation by just changing the intensity of our optical standing wave. For example, in this third direction, we can go from here to here. So it also means we can easily change dimensionality in our problems and basically look how the system behaves as we go from 1D to 2D to 3D in those optical lattices. Okay, so let me start and come to the first system that I would like to look at. Those are fermionic spin mixtures in optical lattices. So basically, most of the time we're talking about optical lattice physics, we describe the systems via the Hubbard model. In our case, we basically just have the tunneling term, so the kinetic energy particles move through the system, and have two spin components denoted here by the sigma index. And we have an interaction between the two spin components. When two particles who spin up and spin down meet at a site, you have an interaction energy plus U. And then something that's additional that can be a nuisance. But actually, I would claim for the optical lattice experiments, it has been of much help that we have these harmonic traps, because otherwise we would have had no chance to realize any of these mod insulating states or reach the low entropy phases that people are looking for. And so we can think a little bit about that, talk about that, but that's just a weak harmonic confinement that underlies this periodic potential that is present in our case, and that's of course very different from real materials, real condensed matter systems. So the topic I would like to talk about is transport properties of these interacting fermions, and see how basically when you turn on interaction, how diffusion breaks down when the system crosses over from a hydrodynamic expansion regime into a ballistic expansion regime, and try to see what we can actually learn during this breakdown of diffusion of the system. So to kind of describe a little bit more our system, I told you we have this periodic potential and we have the harmonic trap. And in our case, we have a combination of a ready-tuned optical lattice and a Bluetooth-tuned, ready-tuned dipole trap and a Bluetooth-tuned optical lattice, which essentially means we can independently tune the depth of the lattice and the harmonic confinement. So that's so far not been possible, but in this experiment we can independently change the depth of the lattice and also independently change the harmonic confinement. So we can basically go from a situation, for example, like this, where we squeeze the system together in the lattice, to a situation where basically we take away the lattice completely, the harmonic trap completely, where the system is really homogeneous, up to some extent, okay, up to some system size, where it can be homogeneous. You know, at the side there will always be some fringe effects, but essentially in the core of the system we can make it extremely flat. We could even make it anti-confining if that's what you're interested in, but that's not what we're going to use for now. Okay, so what we're going to do is to try to see the effect of interactions on the transport properties of Fermi gases in the optical lattice, is try to always create the same initial condition, then turn on interactions and let the gas expand and see how the interactions, depending on whether they're attractive or repulsive, strong or weak, how they affect this expansion. So the experiment we're going to do is the following. We start with a non-interacting Fermi mixture, 50-50 mixture. We squeeze it together by making a tight harmonic trap here into a band insulating state. So now you basically have one fermion per spin state per lattice side. So you just have an up and down fermion on every lattice side, up to some radius. Still non-interacting. Then we basically rapidly make the lattice very deep, so we just freeze out this kind of density distribution. We change the interactions to any value we want, so we set the on-site interaction matrix element. For this condition, this is always the same initial condition so far. Then we lower the barrier and take away the harmonic confinement, so now the system can move. Okay. So what you should keep in mind that it's really important that we always have the same initial condition. It's this band insulating state. We set the interactions and then we let the system expand. So this is kind of schematically depicted here. We create the band insulator, set the interactions, then turn the lattice down and take away the harmonic confinement. So now it's just basically free homogeneous system. We're trying to see how the system expands. This is just a sequence what I told you. So let's just, to get familiarize ourselves with the problem, let's just look at the very trivial problem, what a single localized atom would do if I just have a single spin sitting here localized to that lattice side. Of course, in a band structure picture, I can describe this localized particle as a superposition of all the Bloch waves in my lowest energy band of the system. So it's an equal superposition of all those Bloch waves. Each of those Bloch waves is going to propagate with a certain group velocity in the lattice. And so it means basically if I have a superposition of those states, I will have different velocity components of my wave packet expanding in the lattice. And I will have some maximum velocity, Vmax here, kind of forming the maximum velocity, kind of a front, maximum front that expands in the system. So let's just look at this animation. So we start with the localized atom, we let it go, and this is what it looks like, and how this expansion would look like. And this one would be, of course, this part of the wave function would be the one expanding with this maximum velocity Vmax. Okay. Now if you do this in 2D in a simple cubic lattice, it's basically exactly the same story. You just do it in 2 dimensions. The problem is separable. So basically, from an initial spherical distribution, you get kind of a square distribution corresponding to the different kind of group velocity expansions in the 2 axes, in the x and y axis. Okay, so let's just check if our kind of atoms do that, just as a calibration to see. So these are images of a band insulator in our lattice. It's kind of a 2-dimensional system. We're looking from the top, and we're seeing the band insulator, this dense core. It's kind of spherically symmetric. And now we're letting the system go and see what happens for no interactions in the system. And indeed, as we saw in the simulation, this is also what the atoms do. They change from the spherical distribution to the square distribution, signalizing that it's a ballistic expansion that we're seeing. You're also seeing that for very long times things are going wrong horribly somehow, and this is the case when the atoms start to sample the corrugations and the potential, when the thing is not flat anymore, as I kind of advertised in the beginning. Okay, so we just disregard all this, we just expand only up to this point, it's kind of still reasonably homogeneous, the system. And just to see that it's indeed a ballistic expansion, we can plot the cloud size versus expansion time, deconvolute for the initial size of the system, and you just see kind of, as you would expect in ballistic expansion, the size of the cloud grows linearly in time telling you that you're indeed having a ballistic expansion. Actually, that you see this is quite important also to prove that you don't have any disorder, kind of speckle type disorder in your lattices, which would kind of deviate from this ballistic expansion. So it's also a nice check for us to see that our lattices, even for deep lattice depths, are really kind of nicely flat, and we don't have any disorder in the system. So now let's turn on interactions, and let's see now what happens as we crank up interactions. So here we have the scattering length between our two spin states, and for no interactions after 25 milliseconds, you just get this square as I advertised before. So now we turn on interactions, either go to attractive interactions or to repulsive interactions. And first you see two things. So you don't get a square anymore. You kind of get a bimodal distribution. So you get a kind of core, which is circular, expanding like with a spherical symmetry. And you get wings, which expand in this kind of square symmetry. Also what you see, whether we go to plus 150 A0 or minus 150 A0, doesn't change at all the picture. So although that's kind of a little bit surprising, because imagine this, you start with a gas that has a lot of repulsive interaction energy stored in it, and you let it go, you let it expand to infinity. So all this interaction energy will get converted to kinetic energy eventually in the long run when it expands. So that means that initially when you have a gas with a lot of repulsive interaction energy, all this excess interaction energy is going to be converted into excess kinetic energy. So you're going to end up for large repulsive interactions with a system with a lot of kinetic energy. And for attractive interactions, you need to break up the pairs, so it's going to cost you kinetic energy, so you're going to have much less kinetic energy. Nevertheless, what you see in the lattice, and I'll come back to that point in the end, it's kind of a special novel dynamical symmetry that we found in this Hubbard model. In the lattice, both cases are really exactly the same. And one can prove that mathematically, that they are exactly the same. But it's kind of surprising when you first go through the problem and think about it, that this is a system with a lot of excess kinetic energy, and this lacks kinetic energy, but nevertheless, it looks exactly the same. Here's kind of 3D plots of this showing you again how this behavior changes in the system. What you also see that the expansion rate, so the cloud size divided by time, basically depends very much on the interaction parameter. So U is my interaction, J is my kinetic energy, and it's perfectly symmetric. As I advertised, if you plot this expansion rate is perfectly symmetric around U over J0. Also what you find that mass transport is dramatically slowed down already for very weak interactions. So already when you go to U over J around 1 or 2, which is still a very weakly interacting system for a Hubbard model system, for fermions in this 2D system, the mass transport goes down by almost like an order of magnitude. It's the speed with which the cloud expands. So interactions really have a dramatic effect on the expansion of the transport of these systems, of these fermions in the lattice. Okay, so let me go a little bit into details, into a little bit more maybe mathematical physics discussion on exactly what happens when this kind of diffusive regime breaks down, how we can recover some kind of interesting features back again. So let's try to describe the system by kind of a standard diffusion equation. So when there are a lot of collisions in the core, when there are interactions, the core is very dense, there are a lot of collisions, we believe we can describe the system with a hydrodynamic description, so we just write down a diffusion equation, and in the diffusion constant here, in our case, is simply proportional to 1 over the density of the system in the wings of the cloud. Okay, so that would be just because you have the diffusion constant being proportional to 1 over the number of particles times the number of holes, and if you're out in the wings of the system where n is small, then basically your diffusion constant will scale like 1 over n. This is actually a special case when this diffusion constant scales like 1 over n. If you go into the mathematical physics literature and look at solutions of the diffusion equation, this is a special case of this diffusion equation that people look at, and generally they look at diffusion equations of this form where the diffusion constant scales like 1 over n to the power of delta. And if delta is larger than 0, they call this a fast diffusion regime. When delta is larger than 1, it's super fast diffusion. And when delta is equal to 1, they call this logarithmic diffusion, which would be our case in the wings of the cloud, simply because in that case you can write this as Laplace of log n. Okay. Now this diffusion equation, these type of diffusion equations have kind of very interesting mathematical solutions which are quite puzzling. For example, in 3 dimensions, for delta equal 1, all particles reach infinity after an infinitesimal time. So that's of course a very that's just a mathematical solution. That's of course completely unphysical, and we'll try to use that knowledge to try to understand why diffusion breaks down, how diffusion breaks down. But that's what you get, and it's of course this divergence here that you have in this diffusion constant. In 2 dimensions, delta equal 1. And it's even more interesting. There's basically a universal loss rate for particles to occur at infinite distance. So if you can write your diffusion constant as gamma divided by n, what you will find that the loss rate of particles appearing at infinity it has a lower bound given by this factor gamma. So there's this universal minimum loss rate in the system. Okay, so that's of course unphysical, and what we have to see is how this kind of unphysical behavior is restored in our case. Let me just digress a little bit more. This diffusion equation, actually in mathematics, this is a very famous equation. This is the so-called Ricci flow in mathematics, and has been used by Gregory Perelman to prove the Poincaré conjecture, and basically describes the change of curvature of a manifold governing this kind of diffusion equation. And that's exactly the one we have in our case. Actually there, this universal loss rate that I showed you before in this diffusion equation is just a topological invariant of the system. So if you integrate the number of particles lost, this corresponds just to a topological invariant of this kind of diffusion equation that you see in the system. Okay, so let me come back to the physics. So for no interactions, you saw this ballistic type of expansion, and you basically saw that the system has then this square-like symmetry. For interacting systems, we find basically this crossover. We have this dense core where we have kind of a collisional system, hydrodynamic expansion, and the wings we have a ballistic expansion of the system. And of course, then we have a crossover between the two. And okay, so in order to try to get a little bit more quantitative in the theoretical description, what Achim Grosch and his colleagues in Cologne did for us, they used kind of a Boltzmann type description in relaxation time approximation to describe the evolution of the system. So basically you can write down a differential equation, Boltzmann equation for the density distributions of the system, where the system locally always relaxes to thermal equilibrium in the hydrodynamic regime. And again, this collisional rate is proportional to the density times the number of holes in the system, which I already told you about before. And indeed, if you already look at this, solve this differential equation, which can kind of mediate between the hydrodynamic regime and the ballistic expansion regime, you indeed find this crossover behavior of the spherical symmetry in the center and these ballistic wings in the cloud. And these ballistic wings here at the edge of the system, where the density becomes so small that then the system does not behave hydrodynamic anymore. If we look quantitatively at this expansion rate, so this core expansion velocity versus interactions, we find kind of an interesting property. So if we now look at the following, so imagine, remember, the system looked like this. So you had this ballistic wings, you had a core, and basically what we find is that for kind of turning on the interactions, can make the expansion velocity of this core. So what we're looking at is how does this core, this spherical core, move outward, the edge of this spherical core, actually can turn negative, okay, if you turn on strong enough interactions. So what that essentially means is that basically the core completely gets stuck. It doesn't move at all anymore, and just emits ballistic particles, so just constantly shrinks. So what happens is if you turn on strong enough interactions, what happens over time is that this core, spherical core, shrinks and shrinks and shrinks by emitting ballistic particles, ballistic transport particles, which attract very ballistically. So essentially, for kind of strong enough interactions in the system, you just have a spitting out, the core spitting out these particles, and indeed if you look at the rate at which these particles are emitted, these ballistic particles, it again turns out to be the universal loss rate that we had occurred in our two-dimensional diffusion equation, okay, that is shown up there. So this universal loss rate for the 2D diffusion equation again shows up here in this problem as the universal rate at which particles are emitted by this very dense core for strong interactions in the system. Okay, so of course this breakdown of diffusion we have to expect to occur because we know for a quantum system the maximum current we can have in a lattice is just the velocity, the maximum group velocity we can have times the density of the system. And when of course the diffusion current, the current predicted by the diffusion current, will become larger than this quantum mechanical current, the ballistic current we could have in the system, then of course we have to have a breakdown of this regime of diffusion to ballistic expansion. So it's actually these very details of the system that kind of set the boundary conditions for the differential equation that provide a crucial feedback to the core, diffusively expanding core of our system that kind of holds it together. So it's this very dilute, ballistically expanding cloud which provides a feedback on this diffusive core and limits the expansion velocity of this diffusive core in the system. Okay, just to come back to this U and minus U symmetry point again. So let me just give first an intuitive explanation why it would be the same. And really the lattice is crucial to understand this. So remember, our intuition told us repulsive interactions lead to kind of a positive pressure. So we would expect the system to expand faster. Whereas attractive interactions would kind of hold the system more together. But we saw it was not true. So we saw it's exactly the same thing. So why is this wrong in the lattice? In the lattice it's wrong because we have this very special dispersion relation. So whether, for example, when you have a lot of kinetic energy in the system, so you create a lot of states in the lattice with high quasi-momentum, they expand with exactly the same velocity as the states which have low quasi-momentum here, which would occur, for example, when you break up attractively interacting particles. So for attractive interactions, you mainly populate those low momentum states. For repulsive interactions, you mainly populate the high momentum states, high kinetic energy states. But in a lattice, due to this, in the simple cubic lattice, I should say, due to this special dispersion relation, these expand with exactly the same velocity. So their behavior is exactly the same in the two cases. There's also a formal argument that Eugene Demler wrote down. You can read it in the preprint on this paper, where you basically can show strictly in a mathematical way that for an initial state, and the observable you're looking at, in our case the initial state is a band insulator and the observable is the density, are time invariant, both time invariant, and the system is also invariant under a pi boost of quasi-momentum, which is also the case for our band insulating case. Then for a bipartite lattice, all these observables behave the same for all times for any values of U and minus U, for any pairs of U and minus U. So it's kind of a novel dynamical symmetry that you encounter in the Hubbard model that makes this expansion exactly the same in the two cases.
Okay. Was it that, I mean, this assumes that you have to have a cubic lattice, or?
Yes, so for example on a triangular lattice it does not work. So for a triangular lattice it doesn't work. Also if you have a different initial state, so let's say you have a kind of a metallic state, initial state, you should not see this exactly same expansion behavior for U and minus U symmetry. That's exactly the point.
Would you see something interesting with these Dirac cones in a honeycomb lattice?
That's an interesting question, yeah. You could for sure, I mean, I would say this is a very nice way, just in general, to study transport in lattices. I think it's just a very nice method. You know, to start with your initial state, whether it's now in a triangular or simple cubic lattice, and you let it expand. And what the observable that you're looking at is the cloud size over time. Okay. And now you can add interactions, as we did. You could add disorder, you know, as the next step. You know, you can add now, change the lattice geometry, like you say, look at kind of different lattice geometries, exactly lattices, diagonal lattices, and try to understand in this transport properties what are the effects, now combined effects of U and delta, for example. You can also do this in 1D. Remember, we could have these 1D tubes, so you can make a system of 1D tubes, just expand them in the same way along these tubes, and then again look what happens in the case of interactions, in the case of disorder, and for the case of interactions and disorder, for example, Boris Altschuler and Joe Schlavnikov, they recently had some interesting predictions what would happen in the 1D case. You know, all this just is opened by this general way of analyzing the systems. Okay, so that's just maybe a general method that I'd like to advertise that works, gives us a nice experimental observable, the size of the system over time, and if we just take away the harmonic confinement, which is really for transport a nuisance, so for transport measurements we don't want to have a harmonic confinement, so this is really nice not to have it around and just to work with a flat lattice. So the message is we can do this in the experiment and look at those expansion properties. Okay, so I don't go to the conclusion, I told you that before. So let me switch gears and now come to the second part and talk about expansion or dynamics of Landau-Zener transitions and try to see how we can generalize these for 1D many-body systems. So let me just remind everybody of what these Landau-Zener transitions are about. So let's say you have a two-level system. You have a tuning between the two energies of your system, which you can change, for example, here at a certain rate in the experiment, let's say alpha times t. And then the energies of your system will look like this. And if you have a coupling between the energy levels, then of course you get an avoided crossing. And the Landau-Zener formula tells you, for example, what is the probability to stay on this curve, to be adiabatic on this curve. And the parameter that characterizes the efficiency which you stay adiabatic on this curve is given by the coupling strength squared divided by the ramp rate alpha in your system. Okay, that gives you the fidelity of staying, for example, on this adiabatic curve. So that's two-level system. So now let's try to see what changes if you have a many-body system. And the system I would like to look at now is the following. It's like two coupled one-dimensional gases, Bose gases in our case, that we can tunnel couple. So we can basically make optical lattices where you have two one-dimensional systems just coupled to each other. Then again, two one-dimensional systems coupled to each other, but not coupled between each other. So it's just like an array of these independently coupled 1D systems that we're looking at. And we can change almost all parameters in this system. We can change the tunnel coupling between the tubes. We can change the energy bias between the tubes. We can change the correlation properties of the gas, so each one being a Luttinger liquid. We can change the correlation parameter K, change the chemical potential, and see how that affects the tunneling from one tube to the next tube. Okay? So let's start with the first example, kind of being the simpler one. It's kind of what we call the forward sweep. So imagine these one-dimensional tubes, these one-dimensional systems coming out of the plane of the whiteboard. Okay? And we start in a condition where we first have this left tube filled and the right tube empty. So it's kind of in this biased configuration. Now I change my detuning over time to sweep from this configuration to that configuration, and I ask myself, how many particles have ended up in this right tube? If I would be perfectly adiabatic, then 100% of my particles should end up on the right-hand side of my tube. So I plot like NR versus 2 pi j squared over alpha, which is kind of my single particle Landau-Zener parameter, which I compare to. Remember, j is the tunnel coupling, alpha is the ramp rate. So the slower I am, the smaller alpha is, the larger this value will be. So the more adiabatic I expect to be on this curve. And indeed, you see, for single atoms that we load into those tubes, we can indeed see we have nicely this black line, which kind of nicely follows very closely the Landau-Zener formula, single particle Landau-Zener formula that we expect. So now if you already put two particles in there, what you see is that you can go faster. So for two particles in the tube, you can see you can go obviously faster to transfer a certain percentage of particles to the other side. If you put 100 particles into the tube, you can go even much faster than that. Oops, sorry. Much faster than that, and transferring kind of almost all the particles to the other side. So why is that? Okay, so what's going on that makes you be faster if you have many particles in the system? So let's try to basically understand the system and try to look first in a simple picture, diagonalizing the Hamiltonian now, not of a one-dimensional guide, but let's just say we have two dots, two quantum dots coupled to each other. We have interactions between the particle. I'm just looking for the eigenstates of the system in a what we call the so-called blockade regime, where interactions between the particles are much larger than the tunnel coupling between the dots. Okay? That's what people in Coulomb blockade would call kind of a blockade regime, where interactions strongly dominate over the transport, over the tunneling of the particles on the matter. Now, if you diagonalize your Hamiltonian, do this for 1 atom, 2 atom, 4 atoms, what you find is that in this case, for 1 atom, you just get the standard Landau-Zener picture. For 2 atoms, your single avoided crossing has split into 2 avoided crossings, where particles now tunnel sequentially. So you start with 2, 0, then 1 atom hops to the right-hand side, and then as you increasingly tuning more, the next particle hops to the other side. So it goes like 2, 0, 1, 1, 0, 2. If you have 4 particles, you get 4 avoided crossings in the system, where particles now sequentially tunnel from one tube to the next. So it's really one going after the next. And that's very different if they would be non-interacting. If they would be non-interacting, they would be all going at the same time from the left to the right well. Right? So this splitting of the resonances is actually absolutely essential to make use to understand now why we can go faster in that case. Because if we look at the matrix elements for these avoided crossings in the split resonance regime, what we find is that the resonances, just each one has a bosonic enhancement factor which makes the splitting larger than the single particle splitting in the system. Okay? And if we now calculate the adiabatic transition probability, in the non-interacting case it would be just the single particle probability to the nth power for the n particles that we're transferring. Now in the strongly interacting case, in this interaction blockaded regime, sequential tunneling, we have to multiply the efficiencies of going through each of those avoided crossings. Each one has kind of a larger avoided crossing than the single particle splitting due to this Bose enhancement factor, which allows us to go faster through this avoided crossing. So just to remind again, what's really crucial are the interactions between the particles. If you don't have these interactions, you cannot make use of this enhancement factor in the system. So this sequential tunneling is really crucial to see this enhancement. So we can indeed see this in the experiment. So if we make the system more and more strongly interacting, remember one way for us to do this, let's just sketch this double well, and remember what characterizes whether the system is strongly interacting or not is this ratio U over J, right? And so I can make J small by basically making the barrier deep here. So this would be just the x direction. And if I make my x lattice step deep, then the tunneling will go down and the system will become strongly interacting. So in that case, I expect to be able to go faster. And indeed, if I look at my critical ramp rate, where I can, let's say, transfer a certain fraction of particles to the right-hand side in units of j squared, indeed, I see that I can go faster. The deeper I make the lattice, the stronger interacting the particles become in the system. On the other hand, when you change the correlation properties in the gas, so let's say you would have a Feshbach resonance here to tune the interactions along the waveguide of the system. So basically what would happen then is that you start to deplete the condensate. Okay, so condensate becomes more and more strongly interacting. You get a large depletion out of the condensate. Eventually you drive the system into a TONS or into a mod insulating regime. And in that case, basically, for example, for the mod insulating case, where you just have isolated atoms sitting next to each other deep in the mod insulator, of course all the bosonic enhancement is lost. And it's just like independent particles now sitting next to each other, each one tunneling independently. So as you change the interactions between the particles, as you make the system strongly interacting, the bosonic enhancement is gradually lost, and you recover for very deep lattices here, which changes the interactions between the particles. You recover the single particle result of your system. Okay, so let's go into the reverse sweep, which is kind of even more interesting than this and peculiar than this ground state sweep. So now we do exactly the same thing, and then now we just go the opposite. So what I showed you so far was starting in the lower energy tube, coming out of the plane, and sweeping into this configuration and asking how many particles end here. So now I want to do exactly the opposite. I want to start in the high energy tube, the one which is initially higher in energy. I sweep over and I ask how many end on the other hand of the system, on the other side of the system. And indeed, you know that in a single particle Lagrangian, these situations are completely symmetric. It's exactly the same problem. It's just the lower branch or the upper branch of the Lagrangian transition. In our case, you see two very different things happen. So this is the number of particles we transfer versus the tuning. Here, we do the ground state sweep, you see this S-shaped curve, which is kind of the standard curve for a Lagrangian sweep, where here we just change the final detuning of the system. If you do the reverse sweep, you see actually the opposite, something dramatic happens. So you start, looks like a nice Lagrangian transition. Once you've crossed resonance, however, you have an abrupt change and here, abrupt decay of the system. The system just doesn't follow this nice S-shaped curve anymore. And you don't transfer particles anymore to the right-hand side, and just have a complete breakdown here of the behavior, standard behavior of the system. So what's going on? In order to understand that, actually what's helpful is to look at the attractive interacting case, interactive interaction picture, which was kind of analyzed first, and try to use a kind of Gross-Pedievsky description to understand what's going on in the problem. So let me explain what's plotted here. So here's the energy again of our two levels. This is the detuning, what I call delta in the language of Wu and Yu. And the dashed line is the single particle solution. Okay? The dashed line is just the avoided crossings for a single particle. The solid line is what you get when you start to have increasingly attractive interactions in the system. And the attractive interactions get stronger and stronger and stronger between those two curves here. So you see this is characterized by this parameter C in their language. And what peculiar thing that happens is you can see that beyond a certain critical interaction strength, you get this weird loop in the energy structure of this diagram. Okay, so you have kind of a loop in the energy levels of your system. So now the ground state energy doesn't look like this anymore, but instead it's like this. Develops this loop. Okay. We'll talk a bit what that loop means, but now in the attractive case, it's actually easy to understand why this loop occurs. Because as you sweep the detuning from kind of large negative values to positive values, what happens is that the particles, because of the strong interactions, want to stay together. They want to stay together in a tube rather than tunneling to the other tube, which would make them lose interaction energy. So beyond the critical interaction strength, what happens is the particles stay together in a tube, but then at some point they notice, okay, now this is not the favorable energy solution anymore, this is not the ground state of my system anymore, now I'd rather have all particles be in the other tube, but somehow they are trapped in this energy state of the system, this energy level of the system. So we don't have attractive interactions, and but for us that just means that for repulsive interactions this loop occurs in the excited state and not in the ground state of the system. So it's exactly the same physics, the only difference is that this loop occurs in the excited state of our system. So let's try to just make a very simple kind of mean field description of these 1D systems to get the energetics right of this system. So basically you can write down a mean field Hamiltonian of these coupled tubes. We parameterize the amplitudes in the left and the right wells by the sine gamma theta, gamma half, and cosine gamma half parameters. We can write down the Hamiltonian for the system and plot the energy of the state versus gamma angle, mixing angle for different interaction strengths, nonlinear interaction strengths in the system. So eta equals 0 would be the non-interacting case, and you can see the eigenstates of the system are given by the extrema of this energy level diagram. So the extrema of this curve here would be this state and that state. That's of course what you know, that's just the bonding state, psi L plus psi R, and that's the anti-bonding state here, psi L minus psi R. Okay, so these are the familiar single particle bonding and anti-bonding states of your two modes. Now when you start to increase the interactions in the system, you see exactly what I described before in words happens that the system has these new self-trapped states. So you get this new extrema occurring in the system where all the population stays basically almost in one well of the system, or almost in all of the other well of the system. Okay. So what happens as you sweep your resonance through here, you basically end up at this point, but then something catastrophic happens. So let's now plot this energy levels, this energy versus gamma, for different detuning, so we can follow the track of our atoms as we change the detuning. So we start somehow here, large negative detuning, or zero detuning, so somehow in this initial state. And now I increase my detuning here, so I stay here in this self-trapped solution, but suddenly at this spinodal point of the system, this energy solution suddenly vanishes. Okay, so as you increase the detuning, this energy solution suddenly vanishes, and then basically the system, the condensate is not stable anymore, decays. If there would be no dissipation, it would just rattle around in this energy level diagram here. But of course, since we have one-dimensional quantum gases, we can have dissipation mechanisms via phonon emission, so then we expect the system to decay and emit a lot of phonons in the system. So essentially what happens here, you sweep across resonance, your system gets self-trapped, and suddenly decays as you sweep across this resonance here. And this is exactly what you can see here, what's happening here. So you start to sweep, transfer particles, sweep slightly across resonance, and suddenly you get this breakdown. And this is exactly this breakdown after the system has become self-trapped and reached this spinodal point. So you get this strange behavior of the system, which we call breakdown of adiabaticity, where normally you would say, the slower I go, the better I do in a quantum system. Okay, the better I have, for example, stay in a certain quantum state. For example, the slower I ram, the more I transfer particles into the, for example, right tube in our case. But here we see a complete breakdown of this adiabaticity phenomena. So remember, smaller alpha means sweeping slower, so it means larger values of this on this axis here. And you can see here the number of particles transferred per certain parameter regime exhibits exactly the opposite behavior. So you start out transferring more particles when going slower, but then you transfer less particles. So you're becoming less and less adiabatic as you go slower and slower in the system. So the explanation for that is indeed what I showed you before. So let me just sketch the energy levels. So we have this strange loop in the excited state. The ground state looks like this. If I'm very fast, if I sweep very fast across this resonance, the system is not able to resolve all this energy structure here in between. So basically it just looks like a single particle Landau-Zener crossing. You send in particles here, some show up here, some show up here. This is the initial rise here. All the cores overlap in this initial ramp regime where it all looks like single particle physics. Then you go slower, and then you go slower, and when you go slower, you start to enter into this loop. The system starts to see this loop, and for being slower and slower, more and more enters this loop, and essentially becomes trapped at this point here, where you have a complete breakdown of adiabaticity, where the system then has this catastrophic fate, and you see less and less particles transfer. So this is the regime where basically you have a complete reversal of adiabaticity to what your intuition would tell you. Now you could say, well, somehow this cannot be the whole story because, I mean, it's a finite quantum system, right? If I diagonalize everything, I do an exact diagonalization. If I go extremely slow, I should be able to stay in the most excited state or ground state of the system if I do that. And so what's wrong in this picture is, of course, that this is somehow fishy, right? That energy levels cross here is kind of a little bit strange. So what's really happening here, if we go beyond mean field, is that there's an avoided crossing here. This avoided crossing corresponds to all particles hopping simultaneously from the left to the right well. So it's an nth order hopping process in the Hubbard model, which would have an amplitude j to the n divided by u to the n minus 1. So you can write it like this. J times j over u to the power of n minus 1. And if j over u, if we're in a strongly interacting regime, remember this is a very small number. So the amplitude for this process to happen, this co-tunneling of all particles, is very, very small. So this avoided crossing here is tiny in the experiment. So meaning that we basically never cross here adiabatic. If we could do this, it would be fantastic, because we could basically make a large Schrödinger cat state, because the two states here would be just basically n0 plus 0n and n0 minus 0n at these two tips of those avoided crossings. Okay, but unfortunately, because the coupling is so small, we always go through the system here non-adiabatically, so we always jump in here into the loop.
Well, you may have 3 or 4 particles.
That's true. And then we do see that, and we do see this. For fewer particles, we do see this, and we saw this in earlier experiments before, but if you do this with 2 and 3 particles, you do see that you can cross this adiabatically. You're completely right. But just the nth order process is just so unlikely that you never end there and you enter here. And so that's just to resolve adiabaticity. In the end, that adiabaticity is restored. If you go really, really slowly, then you would indeed go along those curves here from the top curve here to the top curve here, and you know your picture about adiabaticity in a finite quantum system is fine. Okay, so let me switch to this.
Have you thought about doing, or can you do experimentally the bloch oscillation experiment where you build up the loops in the energy relief zone?
So this is just 2 tubes.
Yeah.
Okay, so this is just 2 tubes. I know probably one could do it. I mean, I think Ennio Raimondo tried for some time to do it, but his interaction strength was not large enough in that case. Probably you could do it. I mean, for us this was just, first of all, cleaner to do it that way.
So it's nothing you're planning to do?
Not right now, but it's certainly related, and we just thought by just having isolated tubes, it's cleaner to see this effect in this Landau-Zener type of sweeps that we were looking at.
Yeah.
You're absolutely right. It occurs at the edges of the Briand zone in bloch oscillations too. Has actually been predicted also there. I think almost at the same time as this Kian and Wu paper did. So let me just summarize these conclusions that we can draw for the 1D systems. So you saw for the ground state sweep, you can see sweep faster than the single particle case to transfer atoms. And the reason is that you get Bose enhancement, but only if you have interactions, if you're in this blockade type regime. So if you don't have interactions, you don't get this enhancement, and you just have the same dynamics as a single particle system. If you turn on interactions between the atoms, you basically deplete the condensate, you basically drive the system into, for example, a mod insulating state or a kind of a Tong state, and basically recover just single particle physics, now atoms tunneling independently between different groups. For the inverse sweep, we found this interesting loop structure that develops for larger nonlinearities in the system, which leads to this catastrophic fate of the condensate once it entered this point here, and beyond this point becoming unstable and not becoming a kind of energy solution, minimum energy solution anymore, leading to a decay of the condensate and phonon emission in the system. What I didn't show you, because I want to go to the next topic, was that actually if we also increase interactions in this case here, we can turn off this decay mechanism completely because we can turn off phonon emission, and so basically we can have the system restore again the single particle picture as we did for the ground state photosynthesis. Okay, so let me come to the next topic. That's on really what I think for me one of the most exciting developments in optical lattice quantum gases in the last years is now the ability to be able to see, and I think in the future soon, doing this in the labs already, starting to do this, manipulate atoms on a single site scale and single atom scale in these systems. So there are two experiments on this. The first one was done by Markus Greiner's group, and just recently published our work in Nature in 2010. So let me go a little bit into this and tell you about the history of this single site imaging. So there are basically different methods that people use. The most kind of intuitive way to do things was first pioneered by Dave Weiss' group at Penn State, where he basically loaded atoms from a hot gas, so not a quantum degenerate gas, into a very large spaced lattice with 5 micrometer spacing or 6 micrometer spacing, and used fluorescence imaging to basically make the atoms fluoresce. So you just shine in laser beams. Each atom now fluoresces. It's like a small light bulb. You capture that fluorescence, you image that fluorescence with a high resolution microscope objective, and then you can see these individual atoms. And these are pictures, first pictures from his paper in 2007, where he could see kind of single atoms in the lattice, each bright spot being a single atom in that lattice. Okay? The atoms in the next plane are out of focus because the shallow depth of field that we have with these high-resolution microscope objectives. I'll come back to that point. So there's another plane, but that's out of focus. So only one plane on the 3D cube system is in focus, and you can nicely see each atom.
Is it a single atom or what?
This is single atoms probably, or it could be. This is probably, yeah, this is single atoms because you will see this projection method is the same here.
No, I'm asking whether it's single atom or it's odd number.
It's also projected, so it's odd number. So, but I think since in his case it was so low density filled initially, it was also it's the same thing. We'll come back to this point. So another very interesting experiment. I'm not sure you noticed that that was done actually by one of my colleagues in Mainz, by Herwig Ott, who's now in Kaiserslautern, who actually was the first to use an electron microscope to image a gas of atoms. So really combine the world of electron microscopy with ultra-cold quantum gases. So basic idea is you have your cold quantum gas, your EC sitting here, and you have your electron beam coming here, which can be very finely focused, let's say 100 nanometers or something. It will ionize particles, ionize atoms wherever it hits, and then you just have an ion detector which detects how many ions are created at this point, which is basically proportional to the density of particles in your EC that you have. And then you scan your electron beam, and by scanning it over different points, you build up an image, and if you average over, let's say, 100 images, this is what you see. For example, for a 2D lattice, a beautifully resolved lattice size, lattice spacing 400 nanometers compared to the 5 micrometer here. So this is of course much better for kind of many-body physics applications. This is just too wide spaced for many-body physics. There's just no tunneling between those two wells. Tunnel coupling is basically zero. So it's just independent lattice size. But this is nice. This is the regime we want to work in. It's not single atoms you're seeing here. It's really something like 100 atoms, and also the image is averaged over kind of 100 images to get this kind of quality here. So it's not single atom sensitive yet, but it's a beautiful method and has very, very nice high resolution. So the first one now, Markus Greiner in 2009 showed that you could take this method from Dave Weiss to very high resolution imaging by just using the same approach, just using much higher resolution microscope objectives, and to image kind of single particles in these lattices, which have now a spacing of the order of kind of 500-600 nanometers, which is just the system we want to use in the experiments. So let me tell you about our system. So our experimental setup to do this is different from Marco's setup, but the conceptual ideas are, I think, the same. So what we're doing is basically creating, first of all, a three-dimensional crystal of light by having, again, these 3D standing waves. So one standing wave here, one standing wave here, one standing wave which is reflected off a mirror down here, which serves also as kind of a window through which we can observe the quantum gases at another wavelength. Okay? So basically you get these two-dimensional planes. We have 2D lattices, and from these 2D planes we pick out a single one. By magnetic resonance imaging, we can apply a magnetic gradient field and take out a single two-dimensional plane from this single crystal. Okay? This is important because really our objective only can focus onto a single plane. Because when we want to image at a resolution which is on the order of lambda, our depth of focus is also only going to be on the order of lambda. So the only thing we can see in focus is a single plane. Okay, so we have to get rid of the other planes, and we do this by kind of resonance and magnetic resonance methods. So we slice out a single plane, and we look at this single plane with this high-resolution microscope projective. I'll tell you a bit more about that in a second. And so these are kind of some pictures of a thermal cloud that you can see, and you can see each single atom appearing as a bright, very bright spot in our image that we see on our CCD camera, each one being a single atom in the system. Okay, so how do we proceed in the experiments? So in the experiments we typically do the following. We do our many-body physics experiments at shallow lattice depths, let's say around 10 recoil, something like that, where we prepare the many-body states that we want to look at. Then we rapidly jump to a dramatically deeper lattice. This is just to make sure that we can hold on to the atoms while we illuminate them, while we make them fluoresce. Because we're scattering a lot of photons off them, we're heating them a lot, and in order to not make them escape, the potential has to be very deep in which we hold them. So we jump from a 10 recoil lattice to a 4,000 recoil lattice. Okay, so it's enormously more deep lattice, where the atoms are just held very deep, then we illuminate them with a kind of laser beam to make them fluoresce and take an image like this. And for the fluorescence rate we get of about 60 kilohertz for 1 second kind of detection time, we get around 5,000 photons for each atom. So that's an excellent signal to noise. So 5,000 detected photons for a single atom. You can really unambiguously tell when there's a single atom or not. Okay. Now, Nikolai already alluded to it. There's a twist to this detection method, which was known in the laser cooling community before. That is, if you have two atoms and put them very close to each other and turn on light, the two atoms are lost. So this is not going into the details of this process. This is what we call light-induced collisions. So whenever you have two atoms on the order of a wavelength, optical wavelength close together, you turn on resonant light, the two atoms are lost. Basically, they escape with a lot of kinetic energy and are lost from your system. Okay? This means that our detection method basically always only measures the parity of the atoms in the lattice. So if we have sites with one atom, that will stay, because there's just one there, it's not going to be any loss. If there are two atoms, they're going to be lost, so that's going to end up with 0 atoms. If there are 3 atoms, 2 are going to be lost and 1 is going to remain. Okay, so basically what you're measuring is the density, the population modulation, okay, in these experiments. Okay, that means, for example, that your density in a Bose-Einstein condensate can never, your detected density can never be larger than 0.5. Okay, so you increase the real occupation, let's say increases, this would be the particle occupation per lattice site, continuously increases, and if you have a Poisson distribution on each lattice site, corresponding to a coherent state on each lattice site, the particle number you detect can never exceed 0.5. That's just simple fact of this projection method. Okay? And this is actually what you see here. This is, for example, when we image a BC, it looks really a lot of density fluctuations in the system, a lot of holes in the system that reflect kind of this density fluctuations that we have. I'll come back to that. So how do we know particles are on a lattice? Well, a priori, I don't know. You know, the way we do this, we shine in these laser beams, we interfere them, and I don't know really extremely precisely a priori what the angle was under which I interfered my laser beam. Okay, it was close to 90 degrees, but was it maybe, you know, so we make one standing wave interfering these two beams, one standing wave for interfering these two beams. We don't really know exactly those angles. They're close to 90 degrees, but you know, a tenth of a degree makes a big difference when we want to find the position of the atoms in the lattice. So how do we do this in the experiment? So in order in the experiment to find the axis of the lattice with very high precision, we put artificial grids onto the system. We know the wavelength, you know, it's the laser wavelength, so we know the spacing of the lattice, but we don't know the angle, okay? So what we do is we vary the angle, we put a hypothetical lattice on the system, let's say in the x direction, and we vary the angle of this lattice axis. And then we plot the number of occurrences, fluorescence, let's say counts, that we have, versus the distance on this kind of grid that I put on the system. And you can see, if you look at the width of those peaks that we get, as a function of the angle of how we place our artificial grid, there's a clear minimum corresponding to the case when we exactly found the true lattice axis of the system. Okay, when you just have tilted it a little bit, it will give you kind of broader kind of peaks here. If you found the right axis that corresponds to your experimental system, you can find this, and we can indeed then nail down the right angle to better than a tenth of a degree in our system. And indeed, if you look, you do this in the two directions, and look at these white points, which mark the lattice points, you will see that all the fluorescent spots lie on a white point. So they all come from a discrete grid. Okay? This helps us, this projection method, and this knowledge that the particles are sitting on a lattice, helps us to basically now convert this into digital images. Okay? Which is fantastic from an experimental point of view, because what I can do is I can take an image like this, the real fluorescence image like that, I can run a reconstruction algorithm which puts these two facts of the lattice, the point spread function, into the system, and basically finds where there were atoms in the system, where there were single atoms in the system, or these modulo 2 detected atoms in the system. From that, we get a digital reconstruction of the atom distribution in the lattice. And this, of course, is now fantastic, because it means that this digitized image is free of noise. Okay? So any correlation function you might want to calculate now as a theoretical analysis is fantastic, because now you just have this particle number matrix, which you can run over any analysis method that you want without running into the problems of experimental noise.
Are you saying that well, the particle sitting on the nearest neighbor side has kind of no contribution to kind of confuse that the second side was empty or occupied? There's no experimental resolution, we just can
so we can reconstruct the distribution of 99.5% fidelity, and we check this by creating artificial images. So we start with a known distribution.
No, I'm asking because sometimes you have bright yellow, then it's red, and then it's black. What do you do if it's kind of half, a little bit yellow and mostly red? What do you say?
So what you might, it's, that this is yellow has a reason. This is a single atom, right? Okay? Or this guy here, yeah. That's a reconstructed one. This is a single atom. So you're asking, why is this yellow? Well, because actually our optical resolution is not smaller than the lattice spacing. So our optical resolution is on the order of 700 nanometers. Our lattice spacing is on the order of 532.
So you say it's yellow because nearest neighbor sites are
overlapping. No, absolutely. So actually what happens if you look at you have an atom, it's kind of like a delta function, imaged through our optical system with some point spread function. So this is a distribution of fluorescence that we get from a single atom. The next one on the neighboring side will overlap and will of course yield an increased fluorescence.
Okay, so you first subtract red, then you subtract contributions of red to yellow and see what's red.
What helps us are two things. So if particles would not be on a lattice, and also we could have any populations, we would be lost. We could not reconstruct with very high fidelity the atom number.
No, I'm asking different. So you say, okay, black is black. Then red is singly occupied. So you raise red and their contribution to yellow.
Okay, so actually the protocol, how this works, this reconstruction algorithm, does the following. It goes blockwise through the system. It goes blockwise through the system and tries out different atom number distributions. It knows what fluorescence image they will generate, because we know the point spread function. We know what a single atom is going to do. So we can know, for a given atom number distribution, we can create an artificial kind of reconstruction of the image, and then I can just make the chi-squares, make the difference to my original image, and find the one which has the lowest chi-square. Of course, we don't do this globally on the image, because that would be going through the 1,000 configurations. We don't have the computation power to do that. But if we go blockwise through the system, that's sufficient. We test around 250,000 configurations for each image to reconstruct this with this high fidelity. But to do that with high fidelity really requires knowledge of the particles on a lattice, so I know where fluorescence comes from, it's not a random position, and also that I have this projection method. I can know I only have 0 or 1 atom. That really tremendously helps, even if your spatial resolution is worse than the actual separation between the lattice. You can reconstruct the full image, the full distribution, modulo 2, with extremely high fidelity. Okay, so now let's try this on a strongly correlated many-body state. And for that, these were images. I think I've given this talk probably hundreds of times where I showed these kinds of images. And now that this turns into reality is for something fantastic. After 100 times giving the same talk on this, you can show the real images. So these were images of our original paper. I think Randy Hewlett wrote a accompanying use and abuse article in 2002 on the paper where Nature kind of sketched out what is the atom number distribution in a superfluid or in a mod insulator look like. This is kind of very deep in the mod insulator, U over J very large compared to 1. This is a weakly interacting BEC where you have Bosonian atom number distribution, so a lot of density fluctuations in this system. And okay, just me remind you again, probably you're all familiar with this, that when we go look at the system in the trap, basically what we see as the density distribution in the trap is a cut through the phase diagram if we can apply local density approximation. That's not always kind of reasonable, but most of the times it is. So basically when we look at the radial density profiles in our trap systems, they correspond to cuts through the phase diagram. So for example, if the total chemical potential for your Bose-Hubbard model is such that it's here, then as you go radially outward, you have an n equal 2 shell, then you cross a superfluid, then you have an n equal 1 shell, then you have a superfluid. And as you go very, very strongly interacting, this superfluid shell in between becomes just very, very, very thin, and you basically get this staircase shell wedding cake density distribution of your system. For us, it just means, as you go radially outward, you basically have radial profiles along the radial direction here, R being 0 here, of the system. So here are some images and the digital reconstructions of this kind of superfluid BC and mod insulating regimes. So here's the BC. These are the original images in the top row. Nothing done to them. These are the reconstructed one convoluted with our point spread function to kind of compare to our original images, and these are these digital reconstructions that we get out of them. And you can indeed see already that the BC has a lot of fluctuations. As you increase the particle number in the mod insulator, you can see how this shell structure emerges, how you really get these regions of single occupancy. Then actually here is double occupancy in the center. But remember, that gets projected out as 0. That appears in our images as 0 atoms. And then you get the n equal 3 shell, which again shows up as unity fluorescence again. Okay. Here's kind of a zoom into two images of this. So this is the lattice. Each dark spot represents a position where the algorithm found an atom. And that's kind of really dramatic, I would say. This is, for example, a system with 100 atoms or more, where there's just a single defect in the core of the system. So it's really perfect unit density, only a single defect, and that's due to the finite entropy, finite thermal fluctuations that we have in the system that generates this amount of single particle hole pairs in the system. Here's the n equal 2, n equal 1 mod insulator, the n equal 2 core in the middle, n equal 1 core outside. I should just mention briefly that this has also been done in Marco's group in Harvard. They have slightly higher temperatures. I'll come to in a second to the point how we determine the temperatures of the system. But the main point of both experiments is that they are well below the melting temperature of the mod insulator, where the system starts to dissolve very rapidly, and I'll show some results in that too in a second.
Have you actually looked into this relationship between the number of defects and the temperature? Or is it just a little?
Yeah, I'll come to that. Just kind of wait just a few more slides.
But even at 0 temperature, you also have defects.
Yeah, but not at 0, not at U over J infinity. So we'll come to that. So let me just show you a nice picture. This is just exactly the same picture in 3D, and this digitized distribution reproduced again, just showing the striking differences that we have for a Bose-Einstein condensator with a lot of fluctuations, and the mod insulator where we indeed have these unity plateaus in the system. We have unity density interaction. So let's go a little bit more into the analysis of this data. And in our case, because we have very nice potentials, very nice spherically symmetric potentials, we can average over these kind of contours that you can see here to calculate the average density and also the fluctuation at a certain radius. And remember, a certain radius basically corresponded to a certain chemical potential in the Hubbard model. Okay? So remember in our phase diagram that we had, why I plotted here mu over u and j over u. So I'm now basically here in the regime zero tunneling, so we're almost on the x-axis being to 0. So if I start out here, I basically go in a cut radially outward here, and a certain radial position corresponds to a certain chemical potential, which I can simply determine by knowing my trap frequency. Okay. So here's the average density versus radial position for the case of an n equal 1 mod insulator. This is this yellow curve here. And you can indeed see here you have this zero density, then you have just thermal fluctuations, probably a normal region, and then you have this constant density in the core. This is the n equal 2 mod insulator, where you have this n equal 1 shell with constant density, n equal 1. And then actually the real density would go up to n equal 2, but because of the projection it goes down to n equal 0. And this is the BC. The gray data is the BC I showed you before, which never comes, for the weakly interacting case, never goes above 0.5 because of its Bosonian atom number distribution and its large fluctuations. If I look at the fluctuations, atom squared per site squared, at a certain radial position, you can indeed see that all the fluctuations are concentrated in extremely narrow shells, which are thermal in our case, because basically the tunneling is 0. And the core here is this unit density core with very, very low number fluctuations. Actually, if you go right in the middle here, where the number fluctuations are lowest for the curve here, we should have only like 0.2 or 0.3% effect rate of having a hole occurring at this position where the kind of fluctuations are maximally suppressed. So you see, the fluctuations are concentrated to the borders of going from n equal 1 to n equal 2 shell. That's where a lot of fluctuations happen. This is exactly where you see this. It's not also perfectly circular. All the defects sit mainly here. And these curves are very easily to describe because the system we are looking at in the zero tunneling approximation is very simple to describe. So even we can do it as experimentalists. So in this zero tunneling approximation, basically the system, the partition function, factorizes into on-site partition functions, and you can easily calculate exactly what this, with a thermodynamic model, what these curves should look like. And this is what we can do. We can calculate the occupation probability for a certain temperature, knowing the trapping parameters, we know the interaction energy, and then we can fit these curves to the variance and the density, and from that extract the entropy per particle or the temperature of our quantum gas with very high fidelity. Okay? So this, I would say, is also a milestone result, because nobody really knew what the temperatures were in the lattices. So nobody could really tell you what exactly the temperatures were in the lattice. But by going into this very simple regime of this very strongly interacting gas, where we have a simple theoretical model. I mean, otherwise we'd have to turn to Nikolai to tell us in the finite J system what the systems look at. But in the zero tunneling regime, the model is just as simple as a non-interacting Bose gas. It's just different, but it's just as simple and clear. And we can fit these curves, we can determine with very high precision the temperature of the system. For example, we can tell you that the temperature was, in this case, 0.09 with an error of 0.05, U divided by kV. We can tell you what the chemical potential was of our system. We can tell you how many particles we had in the system, all with very high precision. And this one actually is around 0.007 U over kV, the coldest temperatures that we saw. We can also calculate from that the local entropy and the total entropy for the system. And basically, for example, using these values that I showed you before, the temperatures, we find that the temperature, the entropy per particle that we found for our systems are around 0.34 kV per particle. And this is also basically, I would say, the lowest. Well, first of all, nobody could ever measure this before. And it's also, I think, absolutely the lowest entropies that have been reported. And well, you could say that's tautology, but really, these are the regimes where, if we trust the calculations of Nikolai on quantum magnetic phases, where you should start to see onset of quantum magnetism for example, quantum gas mixtures. So for example, for fermions, there's a big quest currently, to cool the system to low enough densities that you can see an antiferromagnetically ordered phase, which is suggested to occur around log 2/2, which is exactly this 0.35. Okay, log 2 is 0.7, log 2/2 is 0.35. And with the bosons, we can now actually say, first of all, we can measure this with the percent precision. We can really say we're also in the regime where we should start to see onsets of this magnetic ordering phenomena, even for these bosonic quantum gas mixtures. As I told you before, we can plot this now versus chemical potential. All this is universal diagrams. We can determine the temperature from this, entropy per particle, all that you want. Maybe let me just finish off and tell you that we can also see really how the Mott insulator melts. So let's increase temperature. And as we increase temperature, you can see that you have this dramatic proliferation of particle Hall effects in the system. So you get much more particle and Hall effects in this Mott insulator. And this really, you can see nicely in these average curves, average density and average fluctuations. This is the colder one, the gray one here. And as you increase temperature, you can see how the density goes down. You don't have an incompressible phase anymore. You see how fluctuations increase. How you get many more fluctuations now in the kind of usually where the system had no fluctuations before. Fluctuations start to go up, start to broaden. The system just starts to melt because of the proliferation of kind of particle Hall pairs in the system. And this actually happens around this value of 0.2 U. You have a dramatic increase. There's no sharp transition in a Mott insulator, so there's no transition temperature when a Mott insulator melts. But in the trap, if you go above 0.2 U in basically temperature, then the system very rapidly kind of loses its nice kind of incompressible properties, and you probably wouldn't call it the Mott insulator. Okay, so why is this so exciting? Let me just tell you a few words, 2 slides on the prospects of where this can take us. Something we're working on now is to address atoms on single sites, and I didn't bring any slides with me, but we're already seeing that this works. So we have another laser operating on a blue transition rubidium, which now combined with our microscope objective gives us a resolution of 300 nanometers, and that is much better than the spacing, the lattice spacing. So with this blue laser, we can indeed see, you can address single lattice sites. So one thing that we're planning to do is focus this blue laser here and flip, for example, the spin of the single atom on that single lattice site. Any atom you want. So you tell me which atom I should go to, I can go there with my laser and flip the spin of that atom, or do any kind of coherent isolation with a single spin. So you can basically, if you envisage a system like this, you have your atoms, you have holes, you can focus in your laser, flip your spin, and look how this spin perturbation propagates in your system. You can look at one-dimensional quantum gases, where, for example, now you make a density perturbation and see how that density perturbation propagates in the 1D gas, or spin perturbation, and look how the spin perturbation propagates to try to see things like spin charge separation in Luttinger liquids, for example. And also, of course, couple 2D guides together, as I showed you before, and analyze those coupled systems. So there's kind of a whole array. So this is just a simulation, but as you see, the real experiment is getting very close to that. It's just kind of a list of things what one can do. We can try to look at coherent particle-Hall correlations close to critical points. See divergence of correlation lengths close to the quantum phase transition to a Mott insulator. In 1D physics, you can start to think about looking at things like for Tonks gas Friedel oscillations, looking at density-density correlations, spin charge separation that I told you about before in the one-dimensional Luttinger liquids for the dynamic properties. So there's a whole array really of possibilities, and I think we started seeing this now for bosons. We're of course thinking about extending this to fermions, but I think it gives us a completely new handle of analyzing strongly interacting quantum systems, playing with them, analyzing them, measuring correlation functions with, I think, unprecedented precision, as I showed you before. So with that, I think I've said enough. So let me thank you for your attention, and let's stop here.
Questions?
Somehow earlier in your talk you mentioned that in order to do this fluorescence measurement that you make the lattice much deeper.
Yes.
And to me it sounded like a destructive measurement, but here you suggested that we could do dynamics also.
So two things. So the imaging is completely destructive. It's a projection on the density modulo 2. Okay, so it's a local number measurement, modulo 2 is completely destructive. What I'm saying here is that local coherent manipulations, they can be non-destructive, because I'm not saying about imaging a single atom. I'm just saying I would flip the spin of that single atom on a lattice side. That I can do non-destructively. For example, what I can do is just use this laser to shift the resonance frequency between two hyperfine states locally, and then shine in a global microwave field to flip the spin locally. That's a completely just non-destructive process. We don't scatter any photons. Just very, very, very few. So no photon scattering here, just coherent light shifts that we use to kind of differential light shifts we use to address and manipulate. And that we can do, of course, coherently. But of course, when you image, let's say you want to measure spin-charge separation. Let's say so you make a spin perturbation here. So the spin perturbation will propagate outwards, and you want to measure the speed with which it propagates outward. So basically, what you do is you wait some time, then make an image. That image is, of course, completely destructive. Then you will find the spin somewhere. Okay, then, of course, you have to repeat the experiment and repeat it again with always the same initial condition. Build a histogram of where you found the spin. From that, you can deduce a kind of a wave packet maximum, and you can tell what the spin velocity was with which the particle is propagated in this 1D tube.
Is there any hope whatsoever of somehow coming up with non-destructive? I mean, this is extremely fantastic what you're doing, but just sort of out of curiosity. I mean, is it sort of total science fiction that
I mean, I think you would need some kind of cavity, local cavities around each one somehow to do that, what you want to do. Because the phase shift per atom, I mean, what you think, can you do phase contrast imaging? Could you do something like phase contrast imaging with this? The thing is that the phase shift, if you calculate it, the phase shift you get from a single atom is just not enough to be detected above shot noise, photon shot noise. Okay. So that's why people use cavities. So because the single pass phase shift is so small, they bounce it between two mirrors to have an accumulated phase shift, which is much larger, which they can then detect. So the single pass phase shift is too small. So I don't know. So I think really that's going to be difficult. That would be difficult, what you're asking for. But remember, for a lot of things, it's completely okay. I mean, we can, for example, completely manipulate kind of an array of particles. We can make arbitrary potentials kind of on this kind of system, and then measure it after it's detected. But to measure, let's say, 2-time correlators, that's going to be difficult. So to measure, let's say, what's the probability of finding the particle at time t and t prime, that's going to be a little bit difficult.
And is there any hope to get around the modulo 2 problem?
Yeah, so modulo 2, I think there is a way to get around that, and somehow that's at least suggestively sketched here. So modulo 2, we can get around the following way. So remember you had these planes. I talked about the plane. Okay. But remember, there's really also a plane behind it and in front of it. We just cleared it of all atoms, so there's just no atoms there. So what I can do, so let's say I have two particles so let me look now on front. So this would be my lattice side in the plane. This would be a lattice side 1 plane in front, and this would be one lattice side 1 plane behind. Okay. And so what I can do now is basically, let me see if I split this into 2 wells. What happens now if you have repulsive interactions is that one atom goes here and one atom goes here. So now you would have the 2 atoms that were initially on the same lattice side sitting behind each other, but directly in 2 planes behind each other. And our depth of focus is large enough to still image that sharply, but should have a fluorescence increase, twice the fluorescence increase. So I think actually with these superlattice techniques that I didn't go into much detail into, but by just splitting each well into 2 wells, because we have repulsive interactions, it always is this nonlinear beam splitter. It's like kind of a mini one-insulator transition. You go with one atom here and one atom here, exactly one atom here. And now they're behind each other, and you image them behind each other, and what it should look like is then something like this, that you see kind of twice the fluorescence here. But we are not there yet. So we try to, first make use of the interesting stuff you can do, even with the modulo 2 projection.
So my question is quite related to that one, so I'll ask another one. So when you actually pick out one plane, you can do that extremely accurately with this RF technique, so there's no noise at all. residual effects from having atoms in other planes?
Well, so you have to be, of course, so we choose a pulse which is extremely narrow in frequency space, and that we really slice out only one plane. There's, of course, magnetic field noise in the system, which makes it, if we don't stabilize that, would make that efficiency with which we pick a single plane fluctuate. But we always pick a single plane. What helps us, I didn't go into detail with that when we actually do this, what helps us also is that evaporation comes to help in that. So remember, let's think about this vertical standing wave. So these are the planes in the standing wave we're thinking about. And we want to pick out, let's say, this plane. Okay? And let's say the point where we do this, we first load a thermal gas into this array. So the thermal gas occupies like 30 planes. Okay? Then we cut out a single plane. And then we continue evaporation until we reach Bose-Einstein condensate. The reason why we do this transfer in a thermal gas and not once we have the BC or the system we want to analyze is basically because we want to avoid this inefficiency of our transfer process to enter in the detection method. Because any inefficiency of me transferring these atoms into the correct hyperfine state will show up as a defect there. But it's not a real defect, it's just a defect caused by my inefficient transfer. But I don't want to have that. So what I basically do is I transfer the atoms once the gas is still thermal. And then if I have a few atoms around still in the other planes, I don't really care so much because evaporative cooling is going to take them away. They don't thermalize, they just go really up. Because their density is so low, they don't thermalize in evaporative cooling, so they're just taken out. So that helps as well to basically ensure that only a single plane is occupied in the system.
So sorry, so you never actually, you can position it on one plane, it never happens that you get it sort of equally between two planes?
It does happen. So it can happen that if you pick the wrong field gradient, it can happen that you sit between two. So we have to always calibrate where we are, where our planes are. And then they're typically stable for a few hours. So there are small drifts that we're trying to find out what they're due to, maybe residual magnetic field drifts. So it really has to be very, very stable because the spacing here is very tight. It's also just 5 nanometers. If you would have larger spacing, 5 micrometer in the vertical, then things get much easier, of course. Yeah. But we immediately see that. You see, the nice thing with if there are two planes or if there's something behind, it happens that once in a while you get an atom behind it, and you can immediately see that as an twice increase in fluorescence level. So immediately see that in the images where we had atoms in other planes. Because there's a very high chance that one was sitting behind the other one in these images.
So that